So this is the three topics that I'm gonna talk today. Firstly, a review of the basic concept. Secondly, we look into the asset and transient. And thirdly, we'll look into the power quality monitors. So review of the basic concept. So why should we care about power quality? Okay, so if you look at the left-hand side here, all right, mainly it's because of the financial impact. Okay, a lot of time we did not really understood why we need to care. So if we don't really know how much is power quality is causing us, just imagine how much the downtime cost for the industrial, especially like for example, stock exchange market. Okay, anytime there's a downtime for the stock exchange market, it's billions of dollars is gone. Whenever there's a production losses itself, okay, just imagine how much material is lost for cleaning, for discarding, throw away, and then the new materials to bring in, and the number of man hours that is lost while waiting for the cleaning out, for the repairs and everything. Okay, and thirdly, higher energy usage because of the power quality phenomena such as harmonics, power factors, and so on and so forth. And lastly, the higher maintenance cost because of the premature aging of equipment, for example, the harmonics, because of harmonics generating heats that it will start to deteriorate your equipment. Electronics is very scared of heat, just like human being. We are very, very scared of heat. Okay, so the more heat we give it to the power electronics component, the more it will heat up and faster the deteriorate of the equipment itself. Second thing, why should we care about power quality? Is all about safety. Okay, so firstly is that safety of the equipment. The equipment will start to malfunction, before even the lifespan end of the equipment. Sometimes you see the equipment start to showing some sign of deteriorating, and it start to malfunction and all those things. So the question mark is, why is the equipment is showing such an early sign of deterioration? So this could be the reason of the power quality. And secondly is overheating and heat, and also potentially harmonic resonance that could also cause the capacitor to give way and also causing fire. All right. Now, how about how much is the quantified value in the sense that power quality can cause anyone or any facility? Okay, in the study in the US itself, okay, it's estimated to be about 150 billion annual cost of power quality issues. Okay, so it is about 130,000 potential cost of downtime loss in revenue for a facility itself. Okay, so it's estimated to be about 14,000 to 6.5 million an hour. Okay, estimate the range of cost, a downtime cost for mission critical facility. So 14,000 probably for the SME, for the simple manufacturing. 6.5 million per hour is talking about something like the data center, like the stock exchange, or those very critical one. There is a lot of financial involvement. Okay, now, do you know that 80% of the problems originate from the customer side instead of from the utility? Okay, this is what the study have found, that 80% of power quality issues come from the customer side. Okay, now why do they not know why this 80% is coming from them? Very simple reason. A lot of them do not have power quality meters. They have power meters, which is good enough. Sometimes they have energy meters, which is capture the energy consumption, but they do not have power quality meters. This is the key thing. Power quality meters can measure power quality events. Okay, power meters cannot measure power quality events. They only measure to the certain limits. Okay, limitation. We will come to that later on. Okay, 3 to 6% of the amount of manufacturing sales money spent to correct power quality problems. This is what the study has found. And 50% of the amount of mission critical power outages attribute to power quality issues. Okay, so 50% of the mission critical power outages in the facility itself. Okay, chances is that it's coming from the power quality issues. All right, so looking at the black box over here, you can see that the cost of disruption. All right, so typically a semiconductor production, this is what we have found out, that is about 3.8 million per event. Okay, this is how much the wafer, the components, the electronic components that need to be cleared out, the clean up, and then reinstall, and a number of manpower, the man-hour loss, and all those things. This is the amount that is causing. Okay, financial trading 6 million per hour. Okay, data center 750,000 per event. telecommunication like Cynthia and all these things. Just imagine the StarHub downtime for last week or recently in Singapore. That could cost more. I mean, not even 30,000. It could be more than that. All right. Steel works 250,000 per event. Glass industry about 250,000 per event. The list can go on, and you can basically estimate how much is the cost of disruption. Okay, so today we're going to share with you how we can try to avoid all these things by first doing the monitoring, measure the power quality, and understand the phenomena so that you can do the next step on installing and mitigate the solution. Okay, now what is power quality? Okay, so look at the waveforms over there. This is the ideal power quality. In today's world, the ideal quote unquote thing is no longer exists anymore. Okay, you take any measurement at any electrical system, you will see that the waveform may not be so smooth, and the current is definitely no longer sine wave. Okay, and sometimes you're talking about balance and also the waveforms. Still there's a lot of balance, okay, but if you look at the a lot of this facility itself, or sometimes the balancing is also a question mark. Okay, so a disturbance on electrical is on electrical parameter is a power quality problems. Okay, so it can be interruption, transient, frequency variation, and so on and so forth. Okay, so let's take a look at the two power quality standards that's talk about this power quality. First, we look at the IEEE standard 1159. The definition of power quality is talk about the concept of powering and grounding sensitive equipment in a manner that is suitable to the operation of that equipment. We are talking about how do we ground it, how do we operate it in such a way that the equipment can operate on its own without any deterioration first. Second, talking about IEC standard, okay, how do we see this IEC standard? IEC 1000-4, 4 is talking about testing and measurement, -30, okay, and this is basically the power quality monitoring. It says about the characteristic of an electricity at a given point of an electrical system evaluated against a set of reference technical parameters. So IEC very much talking about references to the standard itself, whereas IEEE is talking about how is the practical approach. Okay, so today we are very much focusing on the looking at the information taken from the IEEE standard 1159. Okay, so let's take a look at the typical power quality symptoms that you have in the facility or in your customer's facility or anyone approach you. Okay, if you ask them any of these phenomena, chances is that they may say yes, and they don't know what is the reason behind it. Okay, for example, flickers and blinking lights. Okay, so this is talking about flickers. Transformer issues such as noise, extra hot, and premature failure. This is talking about, chances is talking about harmonics. Okay, and thirdly, panel neutral wiring and other distribution equipment running hot. Okay, so this is talking about harmonics in the neutral wiring and also harmonics that is causing the equipment to deteriorate. Okay, running hot. Printed PCB, printed circuit board PCB failure in dry PLC, industrial PC, and so on and so forth. This is chances that it could be caused by transient, it could be caused by harmonics. Okay, could be sometimes caused by the swell. Okay, breaker trips and dry shutdown. It could be caused by harmonics. It could be caused by transient, and can be caused by voltage as well. Okay, premature motor failure and unexpected equipment shutdown. All right. So again, this is most chances that it could be caused by the transient, okay, and also caused by the harmonics. Contactor dropping out is quite common. All right. Poor network communication, higher utility bills, poor power factors, low system capacity. So all these things are basically a sign, okay, to tell you that the facility are having power quality problems. Okay, so we need to do something about it. So before knowing what is the best solution to apply, firstly we have to do the measurement. Okay, so what kind of measurement we need to use is actually a power quality meter. Okay. Right. So let's take a look at the waveforms for those who are interested in those waveforms. Okay. I believe all of us are engineering in training. So let's take a look at the waveforms, all right, of a typical power quality phenomena. This waveform is taken from the IEEE standard 1159, okay, and I combine them together in the 7 categories. Okay, so under the IEEE standard 1159, they categorize power quality into 7 phenomena. Firstly is a transient. Okay, so transient can be 2 types of transient. There's impulsive transient. Okay, there is one spike. Okay, one direction. Oscillatory transient is bidirectional. Okay, so this one is captured in terms of seconds, milliseconds, nanoseconds, impulsive transient. Oscillatory transient we measure in terms of megahertz. Okay, so any equipment that you have, for example, power quality equipment, if they only tell you one type of measurement, which is either megahertz or nanosecond, it is not enough. We have to know both. Why? Because we have to capture 2 types of transient. One is impulsive and the other one is oscillatory transient. Okay, second category is come under the short duration. Short duration is the duration is 0.5 cycle to 1 minute. Okay, anything fall under this category is under the short duration. So under this short duration, there's 3 different names, okay, and phenomena. One is that voltage set. Voltage set, that means is 0.1 to 0.9 per unit. Okay, voltage swell is 0.5 cycle to 1 minute. Okay, sorry, 1.1 to 1.4 per unit and 0.5 cycle to 1 minute. All right, and interruption is basically anything less than 0.1 per unit. All right, so the next category is under the long duration, which is greater than 1 minute. Okay, voltage interruption we call sustained interruption. Voltage set now we call under voltage. Voltage swell we call over voltage. Okay, next category is voltage imbalance. Okay, so voltage imbalance is where the voltage is no longer balanced. All right, and then this is under the waveforms distortion. So under the waveform distortion, we have 4 categories over here. One is a DC offset. Okay, so DC offset is where your reference is off, it's no longer at 0. Okay, second we have these notches. Harmonics is very common. Any type of non-linear loads, okay, that you have in the facility, for example, wearable speed drive, laptops, computers, heaters, any kind of non-linear loads, you will have harmonics generating. Okay, so there is always a dilemma where you do a lot of energy savings, but at the same time you're contributing a lot of power quality issue into the network itself. Okay, so on one hand you do energy savings, on the other hand you have to take care of the power quality in the electrical network. Okay, and under the voltage distortion, we have this noise. Noise is talking about high frequency riding on top of the fundamental frequency. Okay. On the 6th category is called voltage fluctuation. This is called the flickers. Okay, where the voltage is flowing under the influence of amplitude modulation in a sense. Okay, frequency variation is where your frequency start to varies. This type of phenomena is always happen when you try to synchronize the generator to the utility. Okay. All right. So basically, for the power quality standard itself, okay, let's take a look to 2 type of standards. Okay, one of them is looking at the metering, okay, and the other one is looking at the electrical system. Now, in order to capture the power quality, okay, we need to have real power quality meters. Now, is there any standards govern this power quality meter? The answer is yes. Okay, the first standard that governs the power quality meter is 61000 IE 61-4-30. Okay, under this 61000-4- there are 2 type of classes, Class A and Class S. If you still hear people saying Class B, B is obsolete. Okay, it's no longer exists anymore. Okay, Class A is the highest class of the meter, power quality meter you can have. Okay, in the world. Okay, Class S is meant for survey and statistic. Okay. Now, what's the difference between Class A and Class S? Class A meter, whenever you have a Class A meter, brand A or brand B, the moment they claim that they have a Class A meter, the measurement that they collect at the same timing, at the same point, the readings must be the same. The tolerance is very little. Okay, the value is exactly this is what it means by Class A. Okay, that is the reason why utility are enforcing a lot of this Class A meter. Why? Because whatever reading that you capture is the same reading that they see. They are using a Class A meter. Okay, class S meter, there is a tolerance allowable. Okay, so any meter that is not under this class A or class S, with the value that they capture, there is a discrepancy. Chances is that. All right. So that is the definition of the IEC 61000-4-30 class A and class S power quality meter. Now, in order to be recognized as this class A or class A meter, the meter itself must be tested by these two standards. This standard is called 62586. Okay, dash 2 is a PQ standard, dash 1 is the instrument standard. Okay, so basically your power quality meter, the instrument, for safety, whatever thing is tested under the one. Dash 2 is whatever parameter, or the how to do the calculation, everything is all listed inside 610-4-30 is tested using this standard. Okay, so whenever you see any meters that they claim to have this 61000-4-30, they must be come together with these two reference standards. Okay, if they claim they only have this one without these two, that means they declare themselves. Nobody verify it. Okay, so in order to verify it's a pure class A, then they must come with this declaration of this standard IC 62586. Okay, remember that this is very important. Do not be fooled by anybody saying that, oh, I have a class A meter, but I don't have these testing results. Then it's not a class A meter. All right. Now, under the electrical system itself, okay, we have here a lot of standards available in the market. There could be there are definitely a lot of standards from the local government as well. Like for example, in Singapore, we have this Singapore Transmission Code. In Malaysia, we have the TMB, and in other countries, you have the utility standards as well. Okay, so these are the three generic standards globally. Okay, of course, on top of that, you need to reference to your local standard itself. Okay, so the first three generic standard is EN 5160. Okay, this is the used by European norm. Okay, second is talking about IEEE 519, is talking about harmonics. Okay, harmonics, IEEE standard 519 is very common, quoted by anybody in the industry. And then the last one is talking about IEEE 1159, talking about the power quality monitoring. Okay, now let's take a look at the details about second topics that on this seminar, sag and transient. Okay, so the definition of sag, okay, American we use the word sag, British we use the word dim, so both meaning the same. Okay, so sag, as what I've described just now. Okay, so voltage sag is basically a decrease between 0.1 and 0.9 per unit. Okay, so for those who are not power system guy, per unit is in terms of percentage, in a sense. So 0.9 is 10%, 0.9 is 90%, okay, of your rated voltage. This is how we see it. Okay, all right, so RMS voltage and current in the power system frequency duration 0.5 cycle to 1. Typically values is 0.1 to 0.9 per unit. This is the definition according to IEEE standard 1159. Okay, now, so in the IEEE standard, they do give a recommended terms, because what happens is that whenever there's a voltage dip, okay, how do we tell the severity of this voltage dip? Are we going to say how much it dropped here, or are we going to say how much the remaining voltage over here? So the recommended terms is always talking about the remaining voltage. Okay, so for example, this one from here 100%, it dropped down to left 20%. So we say a sag to 20%. You always remember the half, the cup is half full. Always talking about the remaining voltage. Okay, so that's how you always saying that. It's not how much it dropped, it's how much the remaining voltage. Why? Because the remaining voltage is the one that always tell us whether the equipment can continue to run its operation or not. Okay. Now the source of this voltage sag or dip can be caused by switching of heavy loads, starting of large motor, loose connection, vegetation. That means the tree branches where we have overhead line, okay, transmission line, where the tree touches during the strong wind or strong the thunderstorm weather. Okay, that's where it shorted. All right. animal contact is quite common in the northern hemisphere, or the northern part of the world, where during the winter time animals try to sneak into the transformer room or electrical room to keep themselves warm. This is quite common. Equipment faulty, momentary fault, and circuit breaker clearing. Okay. So the effect basically very straightforward. Equipment reset or reboot, circuit breaker trip due to under voltage or process interrupted. Okay, so let's take a look at this case study over here. All right, so this is a real case study happened in US. So the customer intrusion plant in Virginia, US. Okay, the problem. All right, so let's take a look at the problem. Unexpected disturbances causing light to blink, variable speed drives to trip, and molten polyester to gum out dies and rollers. Okay, and a root cause of the problem: incidental tree contact with overhead power line. Okay, now how do they know about this thing, the root cause? Firstly, you need to have a power quality meter class A after the incoming transformer. This is where your point of measurement, very important. You want to identify whether the root cause or the problem, is it from downstream your facility or is it from upstream the utility? You need to have a point of the metering point, power quality meter class A at this point. Okay, this is very crucial. Okay, without this class A meter, basically you will not know where is the root cause of the problem. Okay, so second layer of metering, we always recommend the main switchboard. So basically from here, okay, we are able to see whether the root cause of the problem, is it from downstream or is it from upstream. Okay, all right, so solution: the plant used the information provided by the waveform capture to strengthen the weak link in the system. The AC drive serving cooling rollers. Drive engineer used the waveform to capture the basic setting on the AC drive control. Okay, all right, so basically this is the root cause. All right, so basically the issue is from the upstream itself. Okay, so this is actually from the second case itself. All right, so the picture is not correct over here. Okay, okay, so let's take a look over here, the second case. Okay, type of customer: industrial segment in the US. Problem symptoms: employees start to experience flickering light and unexpected computer reboots. Okay, so root cause arcing from one phase of the 3-pole knife blade switch mounted upstream on the feeder serving the building. Okay, so they install the power quality meter class A. Okay, from Schneider it will be IO 9000. Okay, and then we have another one which is the PM 8000, which is a class S. So Schneider meters, we have this built-in capability of telling you where is the disturbance direction, confidently telling you whenever there's a fault occur at this point of measurement. Okay, this meter is able to tell you where is the root cause of the problem. Is it from downstream or is it from upstream? Okay, so coupled with the PME software, okay, we are able to provide you immediately, okay, where is the root cause of the problem. Okay, so from here at this point of measurement, you will say that it's from downstream, and then from this point of measurement, this guy will say it's from downstream. So if this guy is saying from upstream, then you don't need to look further downwards. Okay, so for downstream you look here, and then this guy is saying from upstream, straight away we don't have this is the location or the fault. Okay, so just remember, whenever you have the power quality meters, okay, you need to have a software, just like our smartphone. Okay, how the phone is become smart is through the software. The software makes the wonders. Okay, if you put all the phone together without the software, it will be like our traditional phone. Okay, so in order to make the phone to be smart, okay, the software is the one that make it very, very smart in a sense. All right, so same thing over here, meter with the software, you will make the whole system very smart, and the person using it also become smarter in the sense that he's able to identify the root cause of the problem faster than anybody else. Okay, transient. All right, so let's take a look at the transient over here. Okay, so the transient itself, there are two types. One is impulsive, one is oscillatory. Okay, so let's take a look at impulsive. Impulsive is one spike over here. Okay, that means it's a sudden non-power frequency change in the steady state condition of voltage and current that is unidirectional in polarity. That means one directional. So anything that is above zeros up here, it will be at the positive side. anything at the negative will be on the negative side over here. Okay, so the source of it very straightforward, lightning. Okay, so you can damage the telephone, the data, communication interfaces, AC power supply, and the disruption will be system crash and data loss. Okay, second type of transient is oscillatory. So oscillatory is bidirectional over here. Okay, it's a sudden non-power frequency change, okay, in a steady state condition of voltage and current that includes both positive and negative polarity. Okay, so just imagine for this type of oscillatory, any switchings of electrical component will cause a transient. Okay, so this transient is called oscillatory transient. Why? Whenever you switch on capacitor, whenever you switch on the cables and transformer, you will have a transient. Okay, so this transient is causing a bidirectional over here. Okay, current limiting fuse operation, contact and relay closure, load startup and disconnect, all these things can cause oscillatory transient. Okay, so the damage and the disruption is the same as impulsive transient. Okay, just remember, impulsive is one spike, oscillatory is both bidirectional. Impulsive caused by lightning, oscillatory is caused by switching of devices. Okay. Now the impact on transient is quite bad, I would say. Okay, so basically, if the equipment is being exposed to transient phenomena, chances is that it is not able to salvage anymore. That means the equipment is damaged. Okay, so transient voltages even stress equipment insulation, leading to gradual breakdown and abrupt failure of the dielectric. For example, this one, the lean says itself, component damage from a lightning strike down. Okay, you have a damage over here. Okay, industrial facility commonly experience multiple voltage transient every hour that may exceed nominal voltage values by 5 to 10 times. Okay, so understanding and reducing the magnitude and duration of these events will extend the life of equipment. All right. So for example, this part over here, this is the motor winding. Okay. The transient output from the variable speed drive itself can cause the damage to the motor windings. Okay. If the care is not taken care, put in a proper solution. Okay. So let's take a look at the, in order to capture the transient, all right, what is very important is a sample per cycle, the sampling. Okay, so if just take a look at these two transient waveforms over here. Okay, they are both are captured with 64 point per cycle, the lowest point of measurement that you can have for a simple meter. Okay, so this is captured phase A to neutral voltage. Okay, at a 64 point sample per cycle. Okay, and this is the same thing, 64 point per cycle with SPD surge protection devices. Now look at this here over here. Okay, so this one is here. You can see that after the transient event has occurred and this guy captured. Okay, based on this 64 point, basically in one cycle you have 64 points. Okay, so this is the resultant of the 64 point sample per cycle. Okay, so look at the here. Initial polarity of the event out of the voltage signal indicates that the energy being added to the system. Okay, now this is added into the system. Then how about this one? This one is being taken out from the system itself. Okay, so this one will have a misinterpretation for those who want to do further analysis. Okay, all right, so longer duration with sample associated with a slower sample can miss the initial polarity of the event. Why? Because if, for example, if the transient is very fast over here, you only have 64 data to capture. So in that case, a lot of information is missing. Okay, now how about if we take a look at the waveforms that it capture using 512 sample per cycle. Okay, so 512 sample per cycle, as you can see over here, you get more waveforms. Okay, so you have a 512 samples in one cycle. So the information that you see is getting more and more. Okay, now is this sufficient? Okay, question mark is how much information or how accurate do you want to see the transient? Okay, so transients we are talking about less than 0.5 cycle. All right, and the magnitude is very high. Okay, if you have less point to capture, that means a lot of information could be very high up here is disappeared. because you are being limited by the points, number of points that you can capture. Okay, so 512 samples per cycle is equivalent to 32.5 microsecond. Okay, but whenever impulsive transient occurs, we are talking about nanoseconds. Okay, very fast. And also we are talking about megahertz for those oscillatory transient. Okay, so let's take a look. If you have the class A transient dedicated type of power quality meter like ION 9000T, okay, you are able to see the full picture of what is going on over there. Just imagine 64 sample per cycle, you only see a, you know, iceberg of this thing only. A simple, sorry, a simple, let me just do the pen here. Okay, you only can see over here, very simple phenomena over here. Okay, instead of the full phenomena. All right, now for 512, you probably see a bigger one. Okay, and then with this 83,333 points per cycle, that means in one cycle, you can see the full picture of what is going on. Okay, now you convert that into the voltage itself. Okay, 64 sample per cycle, this is what you capture. The information that you capture is about, translate that to voltage is about 865 volts. The TVS, what you see is your 341. Okay, so the more sample you have, the higher the voltage, because the more information that you have, you bend up to be 866 volt, probably 1 volts higher. Okay, and then this one is about 8 volts higher. Now, if you have 83,000 sample per cycles, how much information that you see? Or in other words, how much information you have missed out? Okay, so with that itself, okay, you probably have given the wrong solutions to the customer because your information is not complete. Okay, so in order to capture the transient, we need to have a dedicated power quality meter that has transient capture capability. Okay, so with this 5 megahertz, you are able to capture 83,000 sample per cycle. Okay, so this is how much information that you have for one cycle. Okay, right, so let's look into the power quality meters that we have over here. Okay, so for the demand side and the supply side, okay, to all consumer, the user of no, it's not the utility. Okay, anybody who is the user of electrical, okay, we call it demand side. All right, so this is what we will recommend. Okay, for class A, recommend ion/ion T. Okay, ion, okay, ion 9000 is normal without the transient. It can capture up to 10226 sample per cycle, but it's not dedicated for transient. Okay, in order to capture for the transient itself, then we have this model called ion 9000T. Okay, PM 8000 is a class S. Okay, so for the supply side, the utility, if your customer is a utility guys, okay, they will be using ion 8650 or 8800 or the ion 7400, which is a class S. Okay, so I believe that's all that I have for the comparison. Okay, so let's take a look at the power quality monitors ion 9000. Okay, the differentiating features. First thing, it is a true class class A meter. Okay, 0.1 accuracy. All right, so it's the most accurate meter in the world. Okay, high sampling rate. Okay, 1024 and also 10 megahertz. Just imagine 5 megahertz we can capture 83,000. 10 megahertz, how much more we can capture? It's much more. All right. Patented DDD. DDD stands for disturbance detection direction. Okay, we patented. Okay, it is a very unique feature where by looking at the waveforms itself, this meter is able to tell you at the point of monitoring, okay, whether the disturbances is coming from the upstream or is it coming from the downstream. Okay, high speed transient capture by using 10 megahertz. Okay, power event analysis, we are able to give you the waveforms to the details. Okay, compliance, PQ compliance report. Okay, through the PME, we are able to give you the compliance, whether the site is it comply to EN 5160 or whether the site comply to IEEE standard 519 on the harmonics itself. Okay. Flexible and adaptable with expansion module and IO programmability. Okay, so there's expansion module, all right, and then it can be programmed, and coupled with the PME, you can do wonders with this guy. Large onboard memory and cybersecurity resilient. Now, cybersecurity is a real serious issue. The moment we use software, okay, the moment we use IoT, we are exposed to cybersecurity issues. Okay, people can easily hack in if we don't put in proper kind of measures into it. Okay, so this meter is cyber secure. Okay, and is tested. All right. Multiple concurrent communication port and protocols. Okay, and worldwide presence, years of real application and feedbacks. Okay, so we have all these things built inside this most powerful emitter. Okay, so that we can help the customers, okay, to capture the power quality events, the phenomena, and then to do the proper recommendation and correct sizing, and so on and so forth.